morning. Let's see. Put this over here. And yeah, we're live basically. Alright. So, today, I need to change the title. Day 2. Oh my goodness, why is this so hard to work with? Okay. We got Speedrun of abstract algebra. Today will be number theory and intro group theory. Alright. Let's save that. And let's just get started, I guess. I'm like really tired from yesterday. If y'all can't hear me, speak up or forever hold your silence. So yeah, I will be doing some review later on after the third chapter. I'm going to do some review of just some group theory stuff before we get into the meat of group theory. Alright. I'm already really tired. But yeah, good morning everyone. Let's see how this goes. Alright, equivalence relations. Yeah, I'm gonna be talking really quiet. Alright, the camera already fell. That's nice. That's nice. Okay. How on earth can I hold this? Okay. Well, rather that happen now than later. I don't think it really matters to have that on there, but yeah. So, let's go ahead and hit start on the timer. And this. Alright. Let's get going. So this is chapter 3, which is basically a big review of number theory. But it starts out with equivalence relations. Okay. Alright. Definition of a relation. A relation, squiggle, on a non-empty set S is an equivalence relationship or relation if it satisfies reflexivity is symmetric Transitive. Alright, what's up, y'all? Good morning, or I guess good afternoon, because right now we're just doing number theory, review, and what's it called? And we'll get on to group theory later. But I will say I'm going to try taking it a lot slower today because I'm just very tired from yesterday, and also just I don't need to be sweating too hard on it. I'm in this for the long haul. If I keep going super hard, it'll just burn me out. So I'm going to try to take things easy today, and we'll see how it goes. Thank you, Gurtaj Sinj, or Sinj. Yeah, good evening for you, I guess. Yeah, because you're in India. All right. All right. So now. Okay, so now it's just giving some examples of equivalence relations with geometry, and now let's see, example, let alpha map from S to T, be mapping x, y in S, let x relate with y, mean that alpha of x equals alpha of y. So this is an equivalence relation. And okay, so definition. Now it's giving a definition of a partition. A collection, what is it, fancy P, I don't know how to write this fancy P, of non-empty subsets forms a partition of S provided that it satisfies the union of partitions. So fancy P I equals S, and they're disjoint. Okay. Sing. Okay. Sing. Okay. Sing. Okay. That's cool to know. So, I mean, don't mind me. This isn't going to be as big a deal as the integral video because like it's just going to be tough. So so now it's defining an equivalence class. Okay. equivalence class. Let squiggle be an equivalence relation on a set S. Let A be in S, and let this thing, the equivalent class, equal the set X in S such that A is related to X. This is called the equivalence class. Okay. Alright, now we've got a theorem and a proof for that theorem. So, my goodness, I am so tired. Yeah, the modular stuff should be easy. Like, I should get through it pretty quickly. Like, the main meat of today is going to be the group theory stuff. It's just that you need to know a little bit of number theory for some of the, like, the stuff and later on. I should get some coffee. Sounds like a good idea. Getting coffee. Or just sleeping some more. Okay, hold on. Let me write down this theorem. If squiggle is an equivalence relation on a set S, then the set of equivalence classes of S form a partition of S. Then the converse is true also. Conversely, let fancy P be a partition of S and define a relation squiggle on S by A squiggle B if and only if there is a set P, fancy P, or set in P, a set in fancy P that contains both A and B. Then squiggle is an equivalence relation. Thus, there is an A1-to-1 correspondence between equivalence relations and partition. Okay. Yeah. Do I have a Discord? I should make one. I did make one, and it was just, well, I haven't finished it yet. If you want to add me on Discord, just ask Life Nerd. He can link it to you. Oh my goodness. That is the second mic drop. I look weird from the bottom. Hold up, let's put the mic right here. Jeez. Oh my goodness. Okay, we're gonna put this here, alright? And we're gonna put the microphone like so. Okay, let's go ahead and where can this go? Let's try putting it like right here. Would this be in the way? I think we're good. All right. We're in business, and no more worrying about mic drops. All right, so now we got a proof that the correspondence between equivalence classes, or no, yeah, and partitions. Okay, so let's see. Let's squiggle be equivalent. So I need to prove that they're disjoint. Okay, and it's like without loss of generality. It shows that the equivalence class are the same, so the it's always disjoint. Now assume the converse of the statement. We have a partition. Now we have to show that it's a equivalence class, and by doing that you have to do symmetric Okay. So now that was a proof that A and B is transitive. Alright, so now it just shows. Alright. So now it just gives an example of equivalence classes that are partitions. We have the even and odd numbers for integers. In working with equivalence relation on S, it is often useful to have a complete set of equivalence class representatives. That is, a subset of S containing precisely one element from each equivalence class. So, example. Okay. And this says we'll explore that later on. Now we have another theorem. Let G be a permutation group. On S and define a relation squiggle on S by A squiggle B if and only if alpha of A equals B for some alpha in the permutation group. If that is all true, then squiggle is an equivalence relation. So proof, first has to show reflexivity. Well, G must have an identity element, so identity of A equals A, thus A is symmetric to A, so it is reflexive, or not symmetric, equivalent. Now symmetric. So we have if A and B are in S and A squiggle B, then there exists an alpha in G such that alpha of A equals B, but since G is a group, alpha inverse is in G. And alpha inverse of B equals A. So B equals A. So it's symmetric. Now transitive. Let A, B, C be an S such that A is symmetric, or not symmetric, equal to B, and, or I should say equivalent, that's what it means. B is equivalent to C, then, or related. I think that's how you read it, related. A is related to B and B is related to C, then alpha of A equals B and beta of B equals C for some alpha, beta in G, the group. Because G is a group, beta composed of alpha is in G because it's a permutation group, and so composition, it's closed under the composition. From beta composed of alpha of A equals beta of alpha of A equals beta of B equals C. So now we see that A is related to C, thus transitive, thus it's an equivalence relation. All right. So now it has an example. So in this, it gives a more concrete example. Have S equal 1, 2, 3, 4, 5, and G G equals the set of permutations. We have the identity permutation 1, 2, 5 and 1, 5, 2. Those are inverses of each other. All right. In this case, the equivalence classes are 1, 2, 4, or 1, 2, 5, 3, and 4. So the representatives, the class representatives is 1, 3, 4, because those represent the whole set of equivalence classes. Okay, so I think we're good on equivalence relations. Well, we're now going to do some problems. I will say that I am incredibly tired. Incredibly tired. So, if y'all want to be active in chat, that would greatly boost my energy. But, like, I'm just so tired. Okay. So, problem 1, let S equal the set W, X, Y, Z, and that W is symmetric to Y and Z is symmetric to Y. So which of the following must be true? Oh, I don't even need to write this down. I'm just going to do this in my head real quick, because it's just like definitions and stuff. Okay, which of the following must be true? Okay, actually it might help to write it down. So you have W. It's gonna help to write down the equivalence relation like requirements. We need A is reflexive to A, or reflexivity, and we need that A what is it? Or I guess it would be if A reflects to B, then B is reflective to A, and then if A reflexive, or not reflexive, why do I keep saying that? It's not reflexive, guys. Related to B, and B is related to C, then A is related to C. Something like that. So those are the requirements. So in this case we have W is reflexive to Y, or not reflexive, oh my goodness. And Z is related to Y. So what do we need? So we need reflexivity. So we need A, reflexivity. We need B, and we need transitivity. So B and C. I think. I mean, that seems to be okay. And that's the same question. So now we have an actual question. Thank you, bro, in chat. Oh boy, this problem set's kind of long. I am so tired, cause it's just like, being on stream like keeps me to a commitment, but at the same time, I kind of want to just do it on my own. I'm not sure if I'd be better on my own, but I want to keep doing this. Have it documented. But I really need to sleep. I really do need to sleep. If P, fancy P, equals the partition set 1, 3, 2, 4, 5. Which of the following are true? Well, B is true, because 3 must be given to 3. And I believe C is true. No. Oh, let me check the theorem again. It was contains both A and B. Oh, okay, so 4A is true. Okay. Alright, so we're gonna hopefully get to some proofs. Oh, here we go. This one's a proof. For points with coordinates x1, y1, and x2, y2, in a plane with rectangular coordinate system, have x1, y1, 1 be related to x2, y2, mean that y1 equals y2. So if the y coordinates are the same, prove that squiggle is an equivalence or ER for on the set of points on R2. State clearly the properties of the relation equals on R that are used in the proof. Okay. Yeah, I haven't taken real analysis yet, but linear algebra is pretty good. I'm gonna do real analysis soon. I'll get a wave of energy somehow. Maybe if I go to sleep again or something. So we need to show reflexivity. So x1, y1. On. State clearly the properties. Well, since y1, y2, like basically we're using the reflexivity of R, properties of R, that the equivalence things on R. Okay, this proof was very hand wavy, but I'm not giving up. I really don't want to do it on stream. Like, thank you, Taco. Thank you. I wasn't always a math genius, so you can do it too. Just study smartly. Don't study everything. Just study smartly, basically. What does that mean? Don't spend so much time on the same things. My brain is dead. I need to go somewhere else. I need to study this somewhere else. Would y'all be okay with me ending this stream? Cause I really can't do this. Well, I can if I had more energy. Maybe I need some caffeine, but I at least need some rest too. go ahead and pause the clock. So I am beyond tired. Alright guys, so what I'll do is I'll start up the stream when I'm feeling up to like actually streaming. So I'll see y'all later, and when I'm not gonna force myself to stream, basically, because I'm just way too tired to do this. I'll get back to it in a little bit. All right, see y'all.